doesn't care, it's the data
Okay, so welcome to the last session of today. Will be chaired by Juan Francisco. Just a quick announcement. Today we have this popular Colombian dance show. It's at 7 p.m. That's where we gave you some early dinner. No, there will be dinner. But it will be the Auditorio ABC, the one that we were yesterday, okay? The other thing is that we realized that this room is not appropriate. So we found another conference room. Tomorrow will be Auditorio 10. Is the building number 15, El Saman, on the campus map.
18 on the back.
Yeah, El Saman is 18, is it?
Let me check that.
No, okay, it's 15, I think. So it's 15 meters from the cafeteria. It's very nearby. So we'll lead you there, don't worry.
So is it 15 or El Saman? Which one is the correct date?
It's 8.
No, it's 18.
El Saman is
15 is
Sorry, so I'll send you an email anyway. It's 18 on the campus.
Yeah, it's 18.
Okay, we start the last session today on constraints. We have two speakers. One is Quesada and the other is, I don't know, Subramani or Piotr Wojciechowski. But I don't know if he's here or not. Oh, okay. Then we have the session full. Okay, please.
Okay. Well, this is joint work with Deepak, Mehta and Barrio Sullivan. So I am coming from the Insight Center from Data Analytics in Ireland. And yes, this is about computing preferred relaxation for an uncertifiable quantified constraint satisfaction problem. So, well, let me tell you, I am going to split the presentation into two parts. The first one is going to be a sort of long introduction. And I hope that after that you are going to get the global idea of what the paper is about and what the contribution is about, and after that you can switch off. No, I am kidding. So then I will give you some technical details. Yes, I am happy to answer questions after that. So yes, as I said, this is about quantifying constraint satisfaction problems, and you know that in quantifying constraint satisfaction problem we have we extend the normal constraint satisfaction problem by quantifying universally some variables that we call them uncontrollable variables. So we want to guarantee that independent, regardless of the assignment that we have for those variables, still the constraints are satisfied. So this extra expressivity that we add to the conventional CSPs will allow us to model problems in the area of game theory, VLSI design, and well, other fields. I will focus on this one simply because I know almost nothing about game theory, but I do know there are people here in the audience that know about the subject. So my hope is that they see some value in this paper so that we can establish some sort of collaboration afterwards. So that's actually my real motivation. Okay, so what is the problem we are tackling in this paper? So suppose that we are confronted with an unsatisfiable QCSP. Then the question is, what are the reasons for that QCSP to be unsatisfiable? There can be many. You know, in fact, there can be exponentially many reasons for explaining why that QCSP is unsatisfiable. But then we assume that the user has some preferences, and that the user wants to be confronted first with some explanation first than considering others, because there are some components of this QCSP that are more crucial to the user. And that is why that's what we want to solve here. So we are assuming that we have unsatisfiable QCSP. We assume also that the user has some preferences on the components of that QCSP, and based on those preferences, we compute what the most preferred explanation for that unsatisfiability. So that's the thing. And here, I am going to give you a little motivation coming from VLSI, and before you say so, the example is actually very simple. So I agree with one of my reviewers there that was actually criticizing the simplicity of the example. Yes, you are right. So, yeah. So, but anyway, at least I hope that you get the idea of what are we solving here. So, suppose that we are solving a very complex. We are implementing a very complex circuit, and then okay, we have a group of developers, and we establish subgroups within them, and to each subgroup we assign a part of the implementation. You know, so we give them, this is the global specification, and then we divide or partition the problem into subproblems, and we associate to each group a subproblem, and of course, we also define some access to the resources that they need in order to be able to implement those, to solve those problems. But the problem is that one in particular, that when we are defining the access, okay, we can make mistakes at that level. Maybe the access that we have defined is not consistent with the partition that we have carried out. And given that partition and given that access model that we have defined, maybe it is impossible to achieve the final implementation. So then that's what we want to detect. We want to use our framework to compute that incompatibility in an early stage, and there can be many reasons for that unsatisfiability. Okay, we want to confront the user first with the most relevant one. So, well, okay, so this is basically what I already told you, and then let me jump directly to the sample. Let's suppose that this is the global specification. Sorry, I realize now that the drawings are not looking really nice here. So, but anyway, so you can see that this is the global specification.
It's a partial drawing.
Yes. Okay, that's true. Well, okay, so this is the specification, and then let's suppose that we partition the work like this. Okay, we have two teams, and one is going to be responsible of implementing this bit, and the other one is going to be responsible of implementing this bit. And this group, in order to implement this bit, they have access to these variables. And this group, in order to implement this bit, they have access to all these variables, no? And then, of course, given that the accessibility that we have defined, yes, it is certainly true that we can bring this partial implementation into a full specification that is consistent with this. But what happens if we partition the problem like this? So now, okay, yes, so the first group already finished with the stuff. The partial implementation is this one, and the second group that is responsible of implementing this little box here only have access to these two variables. Well, it's not that difficult to convince you that given that accessibility, then it is impossible to achieve that final implementation, because for this you really need to have access to this variable x8 that you cannot really see here. Sorry for that, but you have to trust me on that. So yes, so that's the issue that we want to detect. So these guys who are here, they defined a necessary condition that needs to be fulfilled in order to guarantee that, in order to achieve, to bring the partial implementation into a full implementation that respects the given specification. And in short, this condition, all what it's saying is, okay, we are going to have B group of, 2B group of variables, B group associated with universal quantification, and B groups associated with existential quantification. And for every box, what we want to ensure that regardless of the values that we associate to the entry, to the input, okay, it is possible to achieve the specified output. So this is a condition that needs to be fulfilled in order to be able to bring the partial implementation into a full implementation. And then the question is, okay, yes, I have my partial implementation, and this is the corresponding QCSP associated to it. And what happens then if that QCSP is unsatisfiable? Okay, there is an issue then. So, and the issue is that, okay, there can be many explanations for that, for that unsatisfiability. So then, what do we do then? So then, the idea is to present the user with the thing that is more relevant to its threat, because definitely in the implementation of the circuit there are some components that are more relevant than other, more crucial than other, and the user really wants to deal with those ones that are more crucial first. Remember, so something that I really want to keep in mind from now on is that when you have a formula that is unsatisfiable, there can be many reasons for that formula to be unsatisfiable, and to make it satisfiable, you have to solve all of them. You see? So yes, you have no issue but solving all of them. What may happen is that while solving one issue, that process may indirectly solve other issues. That may happen. But in the worst case, you might need to deal with every issue separately. Okay? And then, okay, definitely you want to start dealing with the ones that are more crucial. Okay, so that was the 7 minutes or less summary. So now let me go to the technical details. So, okay, I don't want to spend too much time on this. Well, what is a constraint satisfiable problem? In a constraint satisfiable problem, we have variables, we have domains, and we have constraints. Constraint satisfaction problem, sorry. We have constraints, and then in this problem we are interested in finding and assigning to our variables such that all these guys are happy. So that's a very informal definition of constraint satisfaction. Okay, so what happens with quantified CSP? Okay, and then yes, an assignment, a solution is just an assignment to those variables so that what I just said, all those constraints are satisfied, and then in quantified CSPs, the problem becomes more interesting because, okay, we have in CSPs, in normal CSPs, we assume that all the variables are essentially quantified, but in quantified CSP, you also consider universal quantification. And then, when it comes to the semantics of that, okay, the existential one is simple. Okay, we just want to guarantee that there is at least one that satisfies the constraint value in the domain that satisfies the constraint. In the universal quantification, we want to guarantee that all the variables in the domains are happy with are consistent with the constraint. Then, okay, this is a little convention here, just so that you don't get confused. So when the variable, the name of the variable is obvious, we omit it, and then also we might refers to the position of the quantifier. Now, what are requirements of a QCSP? Informally, a requirement are like the components of the QCSP. Are the things that we might want to relax in order to make it to go from an unsatisfiable QCSP into a satisfiable CSP. So that you can think of the requirements as components. And then the realizations of the requirements are all those ways that we have of realizing that particular guy. So I am going to give you an example of that later on. But just when it comes to, so we have three types of requirements. So one is, well, the first type is constraint. See, and then if we want to relax a constraint, okay, we just add to the set of tuples that satisfy the constraint more tuples. So we add more solutions to the constraint. If we want to relax the scope of our universal quantifier, that is the second type of components that we have, or the second type of requirements that we have, okay, what we do is just to remove variables from the domain of the quantifier. You know, the smaller the domain of the quantifier, the weaker it is. And then, if we want to relax the position of a universal quantifier, we just move it to the left. And you see, I will give you an example why moving the quantifier to the left relax that the QCSP. Okay, so yes, so this is a little example here where I am going to show you all this. So suppose the phi over here is a QCSP. Well, it is a QCSP, and you can see that it's unsatisfiable. Why? Because there is no assignment for S1 such that for all assignment of S2, this holds. You know, because here you can really see that well, no all values are multiple of 3, and no all values are multiple of 5. And then therefore, okay, this is an unsatisfiable QCSP. And the question is, how do we make it satisfiable? Okay, we have several options. The first option is, we simply reduce. So let me remember what I wrote here. Okay, so yes. So yeah, we simply reduce the scope of the universal quantifier. So before was this one, now it is going to become this one. So reducing it, as I already said, is making it weaker. And definitely, if we do it like this, now this one becomes satisfiable. You see, because there is a value here. Sorry, this is the domain that we are reducing. So we are removing 10. That is the one that is the multiple of 3. And now that there is at least one guy here that for which all values of S2 are okay. And another way of relaxing the constraint, the QCSP, is by relaxing the constraint directly. So before we have an equality here, now instead of having an inequality, we have an inequality. And we say less than 2. So you can see that this constraint is admitting more values than this one, therefore it's a relaxation. Okay, so just to show what we mean by relaxation there. Now, we can speak about ordering of the relaxations requirements. So, yes, if we are going to say that we're given two relaxations, R1 and R2, yes, we are going to say that R2 is more relaxed than R1. If after replacing this, those ones R2 into the original QCSP, the QCSP that we obtain is more relaxed than the one that we obtain when we replace when we use R1. So basically, yes, you just follow directly from the definition from this from the previous definition. Now, so given QCSP QCSP, well, we define. Sorry, okay, I already said this. Sorry for this. So, okay, this is an example of. It's just that I am repeating my slide, I believe. This is repeated, isn't it? Yeah. So sorry. Okay. This is well. Now let me introduce the notion of original requirements. So, as I said, the requirements are those components of the QCSP that can be relaxed. And then, okay, there are some components that we are going to denote as mandatory. So, these components we don't want them to relax, so we want to keep them like this. And there are others that are okay to relax. So that, and then on this we have, so given an unsatisfiable QCSP. So yes, we are going to define the variables as we already did the domain on those variables, and these are the and the original set of requirements are the original set of elements that I want to relax. So in this particular case, this is going to be our running example, and the original set of requirements that we are going to have here are, well, so we are going to allow ourselves to, for this particular QCSP, we are going to allow ourselves to relax the quantification of S2, or the first constraint, x less than 2, or the second constraint, x2 less than x greater, sorry. So these are the three requirements that we are going to be playing throughout the presentation from now on. So this is the QCSP, and these are the three components that we may want to relax or not. And now the question is, on these requirements, we are going to define the possible ways of relaxing them. For the first requirement, we are going to either keep it as it is or relax it completely. For the second requirement, we are going to do the same, and for the third one, the same. So this is what we call 2-point relaxation. So here, I notice that when we replace the domain of S2 by the empty set, yeah, we are definitely ignoring that universal quantification. You know, so in fact, the pure QCSP becomes a tautology when we do that. And yes, when we do this, when we replace the x less than x1 less than x2 by true, okay, yeah, we are removing that constraint, and similarly for the second one. So this is our relaxation function. And based on that, we are going to compute based on that, we are going to compute the minimal conflicts. Just as a matter of definition also, when I say bottom relaxation, what I mean by bottom relaxation is, okay, the corresponding component that removes completely the original requirement. So then for a given constraint, if I have a constraint, the bottom relaxation of that given constraint is the full Cartesian product over the domain of all its variables. And for a given universal quantifier, the bottom relaxation is what I obtain when I replace the domain by the empty set. Okay? So these are the corresponding bottom relaxation for the first requirement, for the second requirement, and for the third requirement. Now, 5 minutes. Okay. So then okay, maybe we want to go very quickly on this. Now, the notion of instance. What is an instance? An instance is just a point on the Cartesian product of the relaxation function for each variable. And definitely you can see that there are, this is basically defining a partial order on the set of all possible instances, this definition. You see, so given two instances, for example, if in this particular example, we have two requirements, R1 and R2. And yes, I can see that these two instances are incomparable, because I cannot say that this one is more relaxed than this one, or vice versa, but definitely I can say that this one is more relaxed than this one, or I can say that this one is more relaxed than this one. So yes, that's the notion of instance. And then why I am introducing the notion of instances, because a minimal conflict, what we call a minimal conflict, is basically an instance under the relaxation function that makes the QCSP still unsatisfiable, but any further relaxation makes it satisfiable. So that's the crucial bit. So at least well, I am happy you managed to get this basic point. So this is a QCSP that is unsatisfiable. So it's not our running example. And remember that the domain of S1 and S2 and S3 are 1, 2, 3. And definitely we know that, okay, it is unsatisfiable. And if we replace the requirements under this instance, the QCSP is still unsatisfiable. You see? Because definitely there is no S1 such that for all S2, this one holds. And similarly, for the second case, so we call this one two minimal conflict, because if we replace the original QCSP using any of the two, we still obtain a QCSP that is unsatisfiable. But if we relax it further, then the problem becomes satisfiable. And then, as I was trying to explain at the beginning, we have to deal with all the conflicts. So we have to solve both of them. And the question is, okay, which one we solve first? So we assume at this point that the user is giving us some preferences on the requirements. So he's telling us, okay, for me, this requirement is more important than this requirement, and this requirement is more important than this requirement. And we have this input, and taking into account that we have these two conflicts over the unsatisfiable QSP, then we say, okay, this minimal conflict is more important than the second one, because this one involves relaxing constraints that are more important than the second one. So then we extend this further by considering all possible conflicts and defining this partial order model, taking into account the preference given by the user. And yes, when it comes to answering which one is the preferred conflict, it's the third one in that order. So in this particular case, it's easy to see because we have only two conflicts, and we know that there is no any other conflict that is more important than I, therefore I is the most preferred one. So, well, I don't have time to go into the details of the algorithm itself. Well, at least I just was trying to give a global idea of this. But in order to compute the actual preferred conflict, we are relying on an algorithm that was introduced by Juncker in UTVPI back in 2004 for computing minimal conflicts on unsatisfiable CSP. So what we did was to use the same algorithm and extend it into to deal with the notion of quantified CSP. So first, 1 minute. Yes, we consider the basic case where our relaxation function have only two relaxations for every requirement, and then we extended that to deal with relaxation functions that have more than two relaxation per requirement. And then when doing so, we remark that if an order is given on the relaxation of a requirement, okay, the problem actually becomes very, very hard to solve. You know, if there is no order, the problem still can be done in polynomial, because basically you have an equivalent class on the set of preferred conflicts. But if there is order, it is more difficult to solve. And in conclusion, okay, what we have presented here, or what is presented in the paper, is an approach for computing preferred explanation given an unsatisfiable QCSP. We believe that, okay, the additional specificity that QCSP gives you, okay, allows you to express naturally problems in the area both of game theory or design and many others. Yeah, we still need to implement the stuff. This is just theory. So yeah, so that's the step is to really implement it and try it out and see how it works in practice. So that's all.
So, do you have any questions? More?
Can you go back 2 slides?
Yes.
25. I mean, I find it a bit ironic that you say that computing a preferred relaxation is intractable. Solving QCSP is intractable.
Okay, well, thank you for asking that question, yes. So here, I am referring to the number, no, that's an excellent question. I should have actually should have started by that. You know, so of course, solving even a normal CSP is intractable and so forth. Here I am referring to the number of consistency checks that you need to perform in order to compute the preferred relaxation. So the number of consistency checks that it can be polynomial, but of course every consistency check, depending on the CSP, okay, might be intractable or not. So you can have the underlying CSP actually could be polynomial. For example, not in this paper, but in another paper.
What does it mean? It means that you need to do exponentially many consistency checks? What do you mean by intractable here?
Yeah, that you need to carry out an exponential number of consistency checks. That's what I mean. That's what I mean. So, but definitely you might question the applicability of this approach, but actually this approach we have been using this one for dealing with optimization problems, approximation to optimization problems where the underlying CSP is extractable. Yeah, like computing disjoint paths between two nodes. That problem is tractable, and then we want to compute, okay, to maximize the number of pairs on which you want to ensure that. And then you can use QCSP for that. In fact, we just got a constraint paper on that if you are interested in the subject.
So let me ask you another question. So there is another way to explain why QCSP is unsatisfiable, which is if a QCSP is unsatisfiable, I mean its negation is true, right? If it's not true, then the negation is true. If you think of QCSP as solving a game, then if it means that the player does not have a winning strategy, it means that the opponent has a winning strategy.
Yes.
Right? That's what it means. So a way to explain why a QCSP is not true is to present the winning strategy for the opponent. Right? Just the negation of the formula. Okay?
Yes.
So
but then the point is,
what is the relationship between what's called a counter strategy on one hand as an explanation, and this relaxation is an explanation?
I think in fact the answer is in your question, I believe, because there can be more than one winning strategy for the opponent, and then you want to present as an explanation the winning strategy that is more relevant to the user.
Is there a formal connection between winning strategy for the opponent and this relaxation?
Yeah, because the winning strategy for the opponent is actually an explanation for the unsatisfiability of the QCSP, but there can be many. And here, what we want to deal is with the fact that, okay, as there are many, we don't want to present the user with all of them because there can be exponentially many. We want to present the user with the one that is more relevant given the preference that the user has.
More questions? No? Camilo? Camilo? No? Yeah? Okay. There are no more questions?
Okay, so anyway, there is a coffee break.
No.
No! Sorry. No, again, you know, so my real motivation for this is because I do see possibility for collaboration. So I really expect people to see some value in this and establish some collaboration, okay? So.
Okay. Okay, now we have Piotr Wojciechowski, more or less. He will present a graphical theorem of the alternative for UTVPI constraints. One moment, please. We have salido el technical problem. Okay.
¿Por qué no dices esa ventana? Es que ya está muy oscuro, cuando apaga la luz ya muy oscuro. No. ¿Qué es? Así el blackout. Suavecito. Dale. Es que estás como en claro.
Okay, then we continue now.
Para cuando apagamos la luz.
Okay, so I'm gonna. So I'm going to present a algorithm on UTVPI, like I'm going to present a graphical theorem of the alternative for UTVPI constraints.
It's copy over there, the volume there.
Yeah.
Hello.
Okay, so I'm going to present a graphical theorem of the alternative for UTVPI constraints. So I'm going to introduce the constraint system, introduce the motivation for these constraints, then introduce our network construction to use for this theorem of the alternative. I'm going to give our results and then the conclusion. So a UTVPI constraint is a constraint where you have two variables, and the coefficients for the variables are +1, -1, or 0. So you will have 6 possible constraints. You have here where you have 2 of them where you have one positive, one negative coefficient, where you have both positive coefficients, both negative coefficients, and then when one of the coefficients is 0. So you have absolute constraints as well, which are bound on a single variable.
What is the domain of the variables?
The variables are just overall real numbers.
Real? These
Yes.
are real constraints?
Yes, these are real constraints. You can also restrict to integers, and this is one of the, like this, even when restricted to integers, it can be solved in polynomial time. So UTVPI constraints have a use in several problem domains: real-time scheduling, abstract interpretation, program verification, and operations research. So from our construction, we want to produce one of 2 types of certificates: a yes certificate when the problem is satisfiable, and a no certificate when the problem is not. So, for example, here's a feasible system of constraints, and as a yes certificate, you can just give a feasible solution. So 6, 2, 3, and that satisfies both of these constraints. You can also have an infeasible system, with these constraints, and then to show infeasibility, you show that some linear combination of these constraints produces an verifiably unsatisfiable constraint here, like 0 less or equal to -1, which you get by adding all 3 constraints here together. So there's nothing which satisfies this constraint, so there's nothing which satisfies this entire system. So, like, with the theorems of the alternative, like, there's, like, so UTVPI constraints also subsume a system of constraints which is difference constraints, which is just one positive, one negative coefficient. So UTVPI constraints differ from these constraints because in a system of difference constraints, if it's linear feasible, it's automatically integer feasible. UTVPI constraints, you have to consider there's systems which are linearly feasible, but not integer feasible. So if you have these 4 constraints, then you have a linear solution of 1/2, 1/2, but no integer solution. Because these 2 constraints here force the 2 variables to be the same, and these 2 force the 2 variables to sum to 1. So this is the only solution, and it's not an integer. So what we want to do is produce a graphical theorem of the alternative, which is when you're given 2 related systems such that one and only one of those systems is feasible. So to show feasibility for one system, to show the feasibility for one system, you can show the feasibility of the second. So one example of this is for linear systems of constraints, you have Farkas's lemma. One statement of which is that either you have some x for which ax is less or equal to c, or you have some positive y, or you have some positive y such that y transpose a is 0 and yc is less than 0. This y represents the linear combination of constraints which produces an infeasible, unsatisfiable constraint. So some systems can have more specified forms of this theorems of the alternative, which can be represented graphically. So for example, for difference constraints, we can construct a weighted directed graph, where each constraint corresponds to a directed edge from the negative variable to the positive variable, with the weight being the bound for that constraint. And then the system is feasible if and only if that system does not have, that graph does not have a negative cycle. So to show infeasibility, all you need to do is show the negative cycle in that graph. So you can similarly construct a graph for 2 CNF clauses. These aren't linear constraints, but due to their restricted nature, you can also have a graphical representation here, where each clause is represented by 2 unweighted directed edges. And then it's infeasible if and only if, for some variable, the 2 nodes corresponding to that variable are in the same strongly connected component of the graph. Meaning you can derive both a clause with just the positive version of that literal and a clause with just the negative version of that literal. So these 2 clauses together cannot be satisfied. And we also have a similar construction for Ne2SAT, which is 2SAT where each clause has to have 1 positive and 1 negative. So it's not enough to have one this means that unlike for regular 2SAT, you can have a positive is not a satisfying condition anymore. So it's more an XOR now instead of OR in each clause. So why we want to produce certificates is because without certificates you can say that your program is producing the right answer, but without a way to verify it, you have to look into the code and see if it's actually, you have to go in through the code and rigorously show that it's always producing the right answer. If your code also produces a certificate, it's much easier to check that what it's saying the truth when it says this system is satisfiable or this system is unsatisfiable. So we will construct this graph to produce these certificates for UTVPI constraints in the following way. So if we have a clause of the form, if we have a constraint of the form plus xi minus xj, then we provide a directed edge from xj to xi. Similarly for minus xi plus xj. If we have xi plus xj, we produce a so-called white edge between these two variables. And for minus xi minus xj, we produce a black edge between these two variables. So this handles all our 2 coefficient. This handles all the constraints with 2 variables in them. Now we need to handle the absolute constraints, or the 1 variable constraints. So for these, we add in a new node, x0, which basically we can show that will, in any feasible solution, always have the value 0. And then we can add in for the constraint xi less than or equal to c, we can add in the edges x0 to xi and the white edge between x0 and xi. Similarly for the negative xi less than or equal to c, we add in the edge from xi to x0 and a black edge. And then to ensure reachability of all the nodes from this x0 node, we add in these really heavy edges which are guaranteed not to introduce any negative cycles to the graph. So for example, if we have the constraint xi plus x3 less than or equal to 0 becomes this edge here, this constraint becomes this constraint here becomes this constraint here becomes this. The absolute constraint xi less than or equal to 6 becomes these 2 edges between x0 and xi, and then we add in all the heavy edges to ensure reachability. So what we can do, so there are several other graphical constructions for UTVPI constraints. One is produced in Mine's paper, and this one doubles the amount, like each constraint becomes 2 edges, and each variable becomes 2 nodes. And so basically it converts each UTVPI constraint into 2 different constraints, and it basically doubles the size of the graph in the process. So this time this constraint becomes these 2 edges, this one becomes these 2, this one becomes these 2, this one becomes these 2, and then the absolute constraint becomes this single double weight edge between the positive and negative versions of the node corresponding to a variable.
It's a bit fast, you realize? It's a bit fast for us.
Yeah, just wondering if I had enough time for that, but yeah. So a different construction introduced by Reves is similar to our construction in that each UTVPI constraint is represented by a single edge, this time with markings on the endpoints of the edge indicating the coefficient of the corresponding variable. So in this construction we have basically the system of constraints from before becomes this graph here. It's similar to our graph that you have only one edge from x0 to x1 and then no edges from x0 to the other nodes. So this time you aren't guaranteed reachability from x0 to each other node depending on how sparse the graph is. So one thing about our network is that even the so-called directed edges can be, and in some cases have to be traversed from the arrow end to the other end. So calling them directed is a bit of a misnomer, but they add the directed edges for different constraints. But in our graph that you can traverse them in either direction. So one thing with our new edge types is we have to define how paths work in our graph, since we aren't dealing with one type of edge anymore. So paths work by looking at how edges can reduce to a single corresponding edge. So if you have a 2-edge path, like this one here, you can reduce it down to a single edge corresponding to the addition of constraints. However, for some pairs of edges, these constraints aren't UTVPI constraints, so these reductions aren't valid because they don't correspond to edges in the graph. or edges in it, edges that could be produced. So for example, this first one here, white, white, when you add the two corresponding constraints, you get a non-UTVPI constraint because you have three variables and one of the coefficients is not +1, -1, or 0. However, if you have a white-black path, then the xj's, because they have opposite signs, cancel out. So when you add these two constraints together, you still get a UTVPI constraint. So in total, there's these 4 different valid edge reductions. And you can apply edge reductions repeatedly to reduce a path of any length down to a single edge, as long as all the reductions you perform are valid. So if a path reduces down to a valid edge type, then it has the same, you can say the path has the same type as the edge it reduced down to. So you can talk about white paths, black paths, and the gray paths, which correspond to the directed edges. So for example, this path here is a white path because you can reduce it down to this single white edge, because you have a positive coefficient for x1, a positive coefficient for x4, and the coefficients for x2 and x3 cancel out because you have positive and negative for each one. And so now that we have path types, we can define cycle types as well for when the path goes from a vertex to itself. And what we're interested in is negative gray paths, because these correspond to a gray edge from a vertex to itself. And if this edge has negative weight, this corresponds to an unsatisfiable constraint. So this basically provides the basis for our theorem of the alternative. If our graph has a negative gray cycle, then the original system of UTVPI constraints is infeasible. So, yeah, so basically this is what we're saying here, that we have either the system is feasible or there's a gray path from a vertex xi to itself. And in some cases, this gray path is actually a white path from the vertex xi to itself and a black path from vertex xi to itself. And in those cases, the vertex itself is used twice in the path. And we're going to explain later that while we do allow repeated occurrences of vertices and edges, we'll never encounter an edge more than twice along in a reduction, in a negative cycle. So basically, because of the way edge reductions work, if you have a black path from a vertex to itself and a white path from a vertex xi to itself, performing one more reduction will reduce this to a gray path from a vertex xi to itself. And here's an example of that. If we have, like here, we have a black path from xi to itself, a white path from xi to itself. So, and then so we can perform these two reductions to get this two-edge path, perform one additional reduction to get a gray edge from xi to itself. And so this is also this is also the path that we're looking for. So, like as we said before, like if we have this negative gray cycle, then the edges along that cycle sum together to form a contradiction. So if we have an infeasible, so here we have an infeasible system of constraints, adding them all together produces a contradiction here. And if this, so now we need to show the other direction, that if this system is infeasible, then it does indeed have a path of this type. So first we showed, so basically what we first can establish is that if it's infeasible, then we have a set of constraints which add together to form this contradiction. So like here, and then basically, and then what we can do is establish that we can put an order on this summation of constraints so that each point in the summation, we maintain a UTVPI constraint as the sum. Basically, when we introduce a variable, we can then find a constraint, always find a constraint which cancels that variable out of the sum, maintaining a UTVPI constraint. So, and if once we have this order, these constraints then do in fact correspond to the path we're looking for. So basically what we have is that in our graph construction, if the original UTVPI constraint is feasible, we have a feasible solution. If it's infeasible, then our graph has this negative weight gray cycle. And one thing that we can also establish is that this cycle uses no edge more than twice. So, like, if we consider this graph here corresponding to these 6 constraints, then here we have this long cycle which uses the edge, which uses this edge here 3 times. We use it here, here, and here. However, we can break this cycle up into subcycles. So we have a gray subcycle here. These blue edges here correspond to a white subcycle which uses this edge twice, once going out, once going back in. And then we have these red edges here corresponding to a black subcycle. So if we just take these white and black cycles together, ignoring this gray cycle, then this is our new negative cycle, and it only uses this edge twice. And we can repeat this until no edge is used more than twice. So now we can provide an example of how this process, how this reduction, of how basically a negative cycle occurs in the graph and how edge reductions can be used to show this negative cycle reduced down to a single constraint. So if this is our graph, then we have that this path is a negative cycle, and we can establish that as follows. So we start with the 2 edges at the beginning of the path, the edge between x1 and x2 and x2 and x3 marked on the graph as shown, and we can relax these down to a single edge here. We can then proceed through this relaxation each time the edge, like being relaxed, is a valid UTVPI constraint, so it corresponds to one of our edges in the graph. As follows, and then once we can get it down to a single negative weight gray edge, which corresponds to a constraint x1 less than equal to x1 minus x1 less than equal to 1, negative 1, so which is infeasible because this is 0 less than equal to negative 1. So what we have done is we've used this graph construction to create a O of mn time algorithm for proving negative infeasibility. We've now working on implementing and testing this algorithm, like establishing it and comparing its running time to other algorithms for this graph. And what we can also do is look for theorems of the alternative for Horn constraints and see if we can find the shortest cycles in the graph, not just negative weight cycles, but the shortest proofs of infeasibility. Okay.
This is okay. Some questions?
Yes.
You mentioned several prior works.
Yes.
And then it's a bit difficult to say what was the previous state of knowledge and what are your contributions.
So the previous state of knowledge for UTVPI constraints was, for linear solutions, was an O of mn time n plus n space algorithm. And we have gotten an algorithm once at the same time, but we're now seeing if it's more efficient by actually testing it and comparing it to the previous existing algorithms.
So is it just better complexity, or do you think you have a better implementation? You're going to have a better implementation?
We think this might be better in terms of implementation. The complexity in the linear case is the same.
Okay, thank you.
However, in the integer case, which we didn't it's covered here, we prior to our work, the best known algorithm was O of mn plus, like, O of mn plus n squared log n. And we have improved this down to just an O of mn time algorithm. So we have improved the integer case.
Thank you. Some more questions? Are you tired? Do you want to go to see the dance? Okay, thank you, Piotr, very much. Okay, now you have 1 hour for resting. And then at 7 p.m. where we must go?
In the same conference room that yesterday.
The auditorium, the big auditorium?
Yeah, exactly. The auditorium ABC. It's called.
Okay, thank you very much.